Okay, now before we discuss, before we get into anything, let's consider this question. Suppose you have a flat surface. The area of that flat surface, would you say that it's a scalar or a vector? And let me ask you this question on top hat. Okay, so most of you chose scalar, but that is actually the wrong answer. The area of a flat surface is actually a vector. That's a bit counterintuitive, um, but it is a vector. And so if I say that it's a vector, it must have a magnitude and direction. So what direction would an area have? So if this is an area, this is a flat surface, um, its area is a vector. So I'm writing it as a vector. What is the magnitude of the vector? The magnitude of the vector is simply the area itself, like however many square meters or square centimeters that is. So that is the magnitude of the vector. But what about the direction of the vector? The direction of an area vector is taken to be the direction of the normal or perpendicular to that area. That makes sense? So suppose this direction is represented by a unit vector n hat. Unit vector just means a vector of magnitude 1. Suppose I represent this direction with this unit vector n hat, then the full vector area becomes a n hat times a. That clear to all of you? So that is the area vector. The direction of a flat area, flat surface area is the direction of the normal to that area. So if this is the flat surface, the direction of the area vector is this normal. Now you might say that, isn't there a bit of an ambiguity there? Because I could have also taken this normal, the normal which goes the other way. I could have taken that as well, minus n hat. So that then the area would have a direction in the opposite direction, opposite sense. That is an ambiguity. And in general, the context of the problem tells you which normal to take. But there is one time when it's not ambiguous. That is when the area is actually bounding part of the boundary of a closed surface. So just imagine that instead of just being an area, this is a face of a rectangular shape. So now this area is part of the boundary of a closed volume, right? In that case, you should always take the outward directed normal. That makes sense? So if that area is part of the boundary of some closed shape, then you should always take the normal that goes out of that shape. But if it's just a flat area, then you can take either one, either the one normal or the one that points in the opposite direction. And usually the context of the problem will tell you which one is the one to take. Is that clear to all of you? So a flat area can be treated as a vector. The magnitude of this vector is the area itself. So whatever square meters, square inches it is. The direction of the vector is the direction of a normal to that area. And so if you represent that direction with the unit vector n hat, the area vector becomes a times n hat. And the rule is that if the area is if the area is, if the area is part of, I should say part of, if the area is part of a closed surface, that means it encloses a volume, then the direction of n hat is chosen to be outwards. That makes sense? So coming back to this square, if I wanted the area of the direction of the area of this face, then I would choose this normal, not the one that goes into the volume. And the direction of this bottom face would be like this. So if your area is part of a closed surface, then you always want to choose the normal that points outwards. That makes sense? All right. Okay. Now we are going to do a calculation which has nothing to do with electricity and magnetism. But you will see later on why this calculation is relevant. So suppose you have a solid rectangular pipe which has a thickness W and a height H as shown over here. And the pipe is carrying water with velocity v. So the water is moving with a uniform velocity v. Everywhere in the pipe, the velocity of the water is v, right? Okay. All right. I've indicated the direction of the velocity of the water here. Now, here is the question that we want to answer. suppose I draw this imaginary red um, rectangle in the pipe, right, as shown over here. So this imaginary red rectangle has an area A, and it has a width W, uh, length L, right? And it's like this in the pipe. And I want to find out what is the volume of fluid that is passing through this area per unit time. I know the velocity with which the fluid is moving. I want to find out what is the volume of fluid that is crossing this red surface uh, every second. Everybody understand the question? Okay, so how would I answer this question? Well, first thing that you notice is that the um, amount of fluid that's crossing the red area will be exactly equal to the amount of fluid that's crossing this perpendicular area. Let's call this area as A perpendicular. So I've drawn this cross section. A perpendicular is a cross section of the tube that I've drawn over here. And so you can see that the same volume of fluid that's crossing the red surface must also cross A perpendicular. Why? Because suppose the volume of fluid crossing A perpendicular is not the same as the volume of fluid going through A, then there would be some fluid buildup inside this in this triangle wedge shaped object, right? But that cannot happen because we know that fluids are incompressible. So the same volume of fluid that's crossing the perpendicular face must equal the volume of fluid that's crossing the red face. Is that clear to all of you? That's the crux of this whole thing. All right. So let's calculate how. So to answer the question, I simply need to figure out how much fluid is crossing A perpendicular per second, right? So the answer would simply be the amount of fluid crossing A perpendicular. If I can find that, that is the answer to the question. All right. So how do I find that? Well, in the velocity of the fluid is v meters per second, right? So in 1 second, how much fluid is going to cross A perpendicular? It would be a column of fluid which has length v. That is the amount of fluid that will pass through A perpendicular in 1 second, right? And so all I need is the volume of fluid, volume of this column of fluid that goes through A perpendicular in 1 second. Its length is v. Its area is the area of A perpendicular. So it's just going to be v times A perpendicular. And that is the answer. I mean, almost the answer. We just need to massage it a little bit. That clear to all of you? Now, what is A perpendicular? It's height times width, right? All right. Now, we need to express the answer in terms of the area of A, not the area of A perpendicular. And the area of A is L times W, right? What is the relationship between H and L? H is simply L cosine theta. Do you agree with that? So I can plug that in. And so I'm just trying to get rid of the H and express it in terms of L. So V times L times W cosine theta. All I did was I expressed the H as L cosine theta. And so the final step would be L times W is just A. So I get V times A times cosine theta. And that is the answer to the question. How much fluid is passing through the red area per second? The answer is V times the area times cosine theta. Is that clear to all of you? Where theta is this angle between the perpendicular face and the slanted face, right? Everybody with me so far? Anyone have any questions?
What is V?
V is the velocity of the fluid. All right. That clear to all of you? Okay. Now let's try to interpret this. So V is the velocity of the fluid. A is, and so V is a vector, right? A is also a vector. We just learned that areas are vectors. And the direction of the vector A is this normal to the face A, right? Okay. theta is this angle. Now, from geometry, if theta is the angle between H and L, theta will also be the angle between V and A, because V is going to be in this direction. Theta will also be the angle between V and A. That's just a geometrical fact, right? So what we have here is the vector V, the vector A, and cosine of the angle between V and A. What does this remind you of? Two vectors multiplied by the magnitudes of two vectors multiplied by the cosine of the angle between them.
The
Cross
dot
product.
product.
Exactly. So what we just ended up calculating is the dot product of V and A. That makes sense? This quantity is called the flux phi of the vector V over the area A, right? So when you calculate the dot product of a vector with an area, what you get is the flux of that vector over that area. The flux can mean different things, can physically mean different things in different contexts. In this particular context, the flux of the velocity over a certain area is simply a measure of how much fluid is crossing that area per second, because that's what we just calculated. That makes sense? So what is the physical interpretation of the flux of V across A? It is the volume of fluid that is crossing the area A every second. That makes sense to all of you? And that is the interpretation of the flux. So, okay, so just get rid of this clutter here. The dot product V dot A is called the flux, and the symbol for flux is this capital phi. It's written like this. The lowercase phi is written like that. So the symbol for flux is capital phi. Uh, and so the flux of the velocity vector across the area A, which is V dot A, is phi, right? And its physical interpretation, just to repeat myself, is that it's the amount of fluid that is flowing across the area A every second, right? Okay, notice one very important thing about our calculation. So we made two crucial assumptions. One is, of course, that the area is flat, right? And the second assumption that we made is that the velocity is uniform everywhere inside the tube. So it's not true that the velocity is slower near the edges and faster near the center. That's what would happen in a real pipe. But we assume that the velocity is the same everywhere over the area. That makes sense? So these were two crucial assumptions. The velocity is uniform and the surface is flat. So unless these assumptions were true, our calculation would not hold.